This is a diode. If you have used an LED before, that is one type of diode that can emit lights, hence the name light emitting diode. There are many types of diode, but the first question is how actually a diode is made of. A diode is actually made from this, a semiconductor wafers. And here comes another question. What is semiconductor? You probably already know that metal is a conductive material, which means if we have this circuit and we fill this gap with a metal, it will conduct electricity and the lights comes on. If I fill this gap with glass, the light stays off because glass is an insulator. But what happens when we fill this gap with a silicon wafer? The light stays off. So you might think that silicon is insulator, but what if it is being heated up? See, it lights up. The silicon is insulating at room temperature but conducts electricity when it is very hot. This is what we call a semiconductor or separa conductor in Malay, whose conductivity can be changed based on the environment, or half conductor, half insulator. This special ability makes semiconductors perfect for electronics devices because we can easily control the operation of a system by controlling the conductivity of the electronics components. We can control the on and off states of a device without the need for a switch. But what is it exactly about semiconductors that allow them to either conduct or insulate? To answer this question, we need to know that there are two types of semiconductor materials, the intrinsic semiconductor and the extrinsic semiconductor. The intrinsic semiconductor is a pure semiconductor materials usually made up from either silicon, germanium, or gallium arsenide. Silicon or germanium, for example, have 4 valence electrons that can easily bond together like shown here. Assume that this piece of board here is silicon wafer or the semiconductor, and the small boards, the green color here, is the electrons. And since all electrons bond nicely in this wafer, it fits nicely in this board and we can't move it around. Even if we try to move it around, it still can't move. It stuck on its position. But for a material to conduct, these electrons here must be able to free themselves from their bonding, which called the valence bands, to become a free electrons that can move around freely. As you can see here, it can move around freely and randomly. And if we push or if we give potential, or in this case the voltages, the higher potential or the positive voltages at one side and the lower potential on the other sides, the negative voltages on the other sides, then these electrons, these free electrons that moves randomly, can now flow in one direction only, and this flow is what we call the current flowing. So to illustrate the difference between metal or conductor, insulator and semiconductor, so these bonded electrons can be represented as this line here, where this is the energy at which the electron is bonded, which we call as valence band. So in order for material to conduct, these electrons here must be able to free themselves from their bonding to the conduction band here. This line here, it must pass through this line here so that it can be said as conducting. If it cannot surpass this line here, it still cannot conduct electricity. And the spacing of this energy level and how they are filled with electron determines if the material is a conductor or insulator or semiconductor. If there is a huge gap like this between the valence band and the conduction band, it is hard for electrons to jump to the higher level. As you can see here, even I give quite a large energy here, it still cannot get to the conduction band here. So this is why when we try to make a glass or woods conduct electricity, when we add enough energy through the heat to push the electrons to a higher band, but that amount of heat would either melt or break or burn them before it actually conducts. This is true for most insulators because the gap is too high. The amount of energy needed to make them conduct is just too high or too hot. On the other hand, have no gap at all between the valence band and the conduction band. So electrons can move to the conduction band freely anytime whenever we supply voltage. So in other words, current can directly flow when we supply with electricity, and this is true to all conductive materials. Semiconductor, on the other hand, falls somewhere in the middle between the metal or the conductor to the compared to the insulator. So in other words, it has a band gap that is small enough so that electrons can jump to the conduction band when we burn it. So as you can see, it's not that hard for the electrons to reach this conduction band and become free. So when we burn it, current can flow freely. The amount of heat we apply determines how many electrons jump into the conduction band and how much current can flow. When electrons becomes free, it will leave its space here, as you can see, empty, because they leave their bonding and becomes free. And this emptiness here, the black colors here, we call as hole or lubang in Malay. And heat isn't the only way to change the conductivity in a semiconductor. That's why we don't burn our computer every time we want to use it. So how actually we change this state without burning our computer? I will discuss this in the next video. So if you like this video, again, hit the like button and consider yourself subscribing to this channel. Stay safe, stay curious, and stay joyful. I'm Ikhwan. May God bless you. Assalamualaikum.